Hello everyone, my name is Ashkik and I'm going to be talking about a novel Bayesian model that we developed to fit the spectrophotometric data of Hubble and Spitzer space telescopes. So in this talk I'm going to be focusing mostly on two observational astronomy methods. And we know that astronomical objects, including galaxies, emit electromagnetic wave in form of radiation, and one way to observe them is to use different filters, with each filter allowing the light to pass only in a certain wavelength range. And by combining the information from the different filters, we can gain a lot of insight about the underlying physical mechanisms that are happening in these astronomical targets. So here on the left panel you can see three images taken from Hubble Space Telescope for the same field of view, and I deliberately colored them with red, green and blue depending on the wavelengths that I'm using for each one of the filters. And if I move forward and combine them into a RGB image, you can see that we have a variety of color across the galaxies, and some of them are more yellowish, some of them are red, and some of them are blue. And this means that these galaxies are emitting different ratio of the fluxes in each one of these filters. And this color can be tied to physical mechanisms that are happening in these galaxies, mostly their stars and dust. So before moving on, let's pause for a second and appreciate how awesome Hubble Space Telescope is. So the distance scale that you can see on these images are 10 arcsecond, and each arcsecond is 1/3600 degrees. The most familiar object in night sky is Moon, and it extends around 0.5 degrees squared. So as you can see, these images are from a very tiny patch on night sky, yet Hubble is able to resolve a lot of galaxies and stars in its small field of view. So the second mode of observing that I'm going to be talking about is Grism spectroscopy. So unlike imaging, in Grism spectroscopy, we are interested to know the flux as a function of very small wavelength beams. And one way to achieve that is to use a combination of prism and grating. Therefore, it's called Grism. And the mechanism is pretty similar to how a prism works. So when light that has different components in different wavelength hits a prism, it gets dispersed, and you can see various components, each one corresponding to different wavelengths. So that's what happened with the Hubble Grism spectroscopy, as you can see in the top panel. The good thing about the Grism spectroscopy with Hubble is that you can still preserve spatial information to some extent along the y-axis, whereas the x-axis after the calibration is going to be the wavelength information. So more familiar way to think about Grism spectroscopy is to collapse the information along the spatial information and get a 1D spectrum, as you can see in the bottom panel. So in the bottom panel, the y-axis is the flux and x-axis is the wavelength, and you can see many features there. Most notably, you can see two troughs here, and these are corresponding to absorption lines from a very specific transition in hydrogen atom. And these two absorption lines can be tied to many physical mechanisms and many parameters of the underlying galaxy, including age. So moving on, our goal is to combine all the information from the imaging and spectroscopy to understand distant quiescent galaxies. So quiescent galaxies, specifically distant quiescent galaxies, are galaxies that formed a lot of stars very early in the universe, and then they stopped forming stars. And it's not clear what is the physical mechanism that lead to the quenching of a star formation in the quiescent galaxies. Our goal is to basically try to understand quiescent galaxies and try to understand what is the physical mechanism that are happening in the quiescent galaxies. And one way to go about and study these targets is to look at the spatial variation of the age of the stellar population. And in order to do that, I'm part of a larger Requiem Galaxy survey, and we use strongly lensed quiescent galaxies, and we combine the boost that we get from a strong gravitational lensing to spatially resolve these galaxies. And you can go and read more about the different sciences that are being considered as a part of this collaboration in the webpage of the collaboration. But we basically pick 8 targets, and we would like to study the spatial variation in the age of stellar population or population of stars in these galaxies. So after picking the targets, we need to observe them. And we observe them using Hubble and Spitzer space telescope. And we also have a ton of data from the past observation, all publicly available. And we're going to combine all this new and old observational data to study these galaxies. And the last step is to basically reduce data and just fit the stellar population and constrain the age. And for that, we use a variety of software, and PyMC3 is one of them. So let's take a few step backs and look at the physical models. So let's assume for a second that we have a very, very simple galaxy, and all the stars in this galaxy basically are formed at an instant. And then what you have is just an aging population of stars. So as you can see in the left panel, the flux of these galaxies as a function of wavelength, this simple population of stars in this galaxy as a function of wavelengths, changes when it gets older and older, and you have less blue light in the wavelengths of smaller than 0.1 micron as the stellar population gets older. Also, you can see a lot less absorption lines in this spectrum. And these two information allow us to basically constrain our main parameter of interest, which is age. But we have to realize that this spectrum and these fluxes are also depend on a parameter called metallicity. So metallicity is basically all the elements that you have that are heavier than helium in a galaxy. And by changing metallicity, this spectrum will change. But we're not interested primarily to measure metallicity. So metallicity is going to be a nuisance parameter. The second nuisance parameter is dust. And dust is a certain molecule in a galaxy, and it also can change the shape of this spectrum. And we also treat dust as a nuisance parameter because we are mainly interested in measuring ages. And finally, we know that the simple stellar population, or SSPs, are not going to be a realistic model for galaxies. And a typical galaxy can have a lot of stars with different ages. So it's proven that we can model a galaxy by using a linear combination of these SSPs. And that's what we're going to do. And the main parameter that we are trying to infer are going to be the weight of each one of these SSPs in our final fit. Okay, so after explaining the physical model, I'm going to be focusing for a second on data. So as I mentioned, we're going to be fitting Hubble and Spitzer space telescope data. So on the top left panel, you can see the HST imaging in the F160 band. On the top right, you can see the HST Grism spectroscopy. And on the bottom panel, you can see the Spitzer IRAC channel 1 observation. So one thing that is immediately clear from this image is that the Spitzer image is more blurry comparing to HST image, and that's because it's relatively have a lower resolution. And this resolution mismatch is something that we need to consider in our statistical model if we want to fit all of these data together. So let's build a model. So first step is to model a spectroscopy. So to model a spectroscopy, we start with the Hubble image. So you can see the image in the top left panel, and this is the F160 image. And since we want to study the spatial variation in age, we define a spatial bins throughout this galaxy. And the pixels that belong to each one of these spatial bins are denoted with different colors in that image. And one thing that I would like to highlight is that the distance from the center for each one of these bins are reported in the kiloparsec units. And a kiloparsec is equal to 1,000 parsecs, and each parsec is 3 light years approximately. And after having and defining these bins, we basically need another component, and those were the SSPs that we defined and explained in the last slide. And we're going to be using mostly 50 SSPs here, and these 50 SSPs are corresponding to 15 ages. And then we have an awesome software, Grism, developed by one of my collaborators, and it is designed to manipulate the HST images and also simulate the Grism spectroscopy. So the main input are going to be the image, the HST image, and also these SSPs, and we input them into Grism, and it generates a model for the spectroscopic data in 2 dimensions. And to generate the SSPs, we can also use the model called Flexible Stellar Population Synthesis Model, which is also wrapped in Python, and all of these are open source software packages that you can check out in the GitHub and start using them. So after inputting all this information in Grism, we're going to have a model for our data. And to infer all the fluxes for each one of these spectroscopic pixels, which I denoted with yi, given the weights of these SSPs, which is beta, we're going to use a normal distribution as it is shown here. And one thing that is important to note is that we only are able to finally sample the SSPs in the age space and use 50 templates and basically 50 free parameters because we have a NOT sampler. And if you want to go and use kind of like the Metropolis Hastings samplers, it's not going to be possible to basically sample the posterior of all these parameters at once. And it's going to be very hard to get a convergent chain. Noting that there is also another complication arising here because it's true that we can define the spatial bins in the imaging, but we only can compare the global spectrum with our data. In other words, we cannot go and identify pixels that belong to each one of these bins in the 2D Grism image. So that's why that after having the Grism model for each one of these spatial bins, we have to sum over them. And that's why you have the summation over J in the formula that you see. Okay, moving on, the next step is to model the HST photometry. That's very easy because we already identified the pixels that belong to each spatial bin. And what we do is to just go and in our data, basically very loosely speaking, sum over the flux that we see, and that's going to be our data. And we also can estimate uncertainty from the HST images, which I'm not going to go into. And on the model side, we can also use the different filter band passes and these SSPs that we already generated to measure the photometric fluxes. And then, since there is no complication here and everything is spatially resolved, we have kind of like a very simple normal distribution for each one of these photometric measurements given the weights beta. So for a Spitzer, it's pretty much the same thing as HST photometry, but the problem is that we cannot spatially resolve the bins in the Spitzer. And so we adopt kind of like a similar approach to 2D Grism spectroscopy. We generate and calculate the flux for each one of these models, for each one of these spatial bins, and then we sum over them and compare the total flux of the galaxy that we see to the total flux that it is observed. And that's why you can see another summation over J in the formula that is shown in the bottom panel. All right, so we have our model and data and everything is set. Now let's concentrate on nuisance parameters. So as I mentioned, dust and metallicity are going to be nuisance parameters. So one way to fit them and to basically have a handle on them in our final statistical model is to fit them first using Prospector. So Prospector is a software that fits photometric data points and it generates posterior for a variety of parameters including dust and metallicity. And it's also an open source software and you're more than welcome to go check it out through the GitHub links that are shown here. And we basically take the posterior of dust and metallicity and use it as a prior to generate the SSPs. And the way to do that is to basically divide this plane, this two-dimensional plane, to 12 boxes. And in each one of these boxes, we draw randomly 15 to 20 values of dust and metallicity and use them to generate the templates, the SSPs, and then average over them. So for each one of these boxes, we're going to have a set of SSPs. And then we're going to assign a weight to each one of these boxes, and these weights are going to be determined through a stick-breaking Dirichlet process. And it's rather trivial to do that for the photometry of HST photometry because everything is spatially resolved, and for each one of the bins you assign your weights and try to determine that through a Dirichlet process. And what you're going to have as an end result is going to be a mixture model as is shown in the first formula there. For a Spitzer and for the Grism spectroscopy, it's going to be a little bit more complicated. And here I adopted a simplifying assumption, assuming that the final template of models that we're going to see and we're going to deal with in this Spitzer photometry and basically the Grism spectroscopy is just a linear combination of all the 12 SSPs weighted by the weight that we see from the Dirichlet process as it is shown in the two bottom formulas. And for the global analysis, if you forget about the spatial bins and just consider the global analysis, none of these complication arises, and I can test these two approaches. The mixture model for all three components versus the mixture model only for HST, and these kind of like simplifying assumption for a Spitzer and Grism spectroscopy. And I basically can test the output and posterior of the parameters for these two models for the global analysis, and then I checked explicitly that what I get is consistent in terms of the posterior. So it's not a very bad assumption. And the main reason behind this assumption is that to basically reduce the computational cost, because it's going to get a little bit complicated and a little bit costly to model everything to the mixture model for a lot of pixels in the spectroscopy that we are dealing with. Okay, so moving on, let's look at the code snippet that is developed in PyMC 3. So first off, I would like you to pay attention to the most important prior here, which is the prior on the beta, or the weights of these SSPs. And this beta can be related to a very important parameter called a star formation rate, or SFR. And I assume that the logarithm of SFR is going to follow a priori autoregressive model with lag 2, as it is shown there. And it needs to be justified, and I'm going to get back to this point later on. So the second important prior is the stick-breaking Dirichlet process for the nuisance parameter, which I explained. And it's going to use a helper function, which is basically the translation of the textbook definition of this process. And I assume that there's also a beta distribution that are going to predetermine these unnormalized weights. And the alpha in this beta distribution is itself following the gamma distribution, as it is shown there. And the whole thing is basically tries to say that the alpha on average is around 1/12. And remember that we had 12 boxes. So it's going to be saying that on average and a priori, what we have is basically the same weight in all the 12 boxes. So moving on, we also have another set of parameters related to emission lines, contamination, and calibration mismatches between photometry and spectroscopy. And these are very important parameters to make the whole thing work from the astrophysics point of view, but I'm not going to be really talking about them, but they're there to make the whole thing work. And then we have the spectroscopic likelihood, which is pretty much the same thing that I showed in terms of the formulas translated into a PyMC 3 code. And to get a faster code, I basically used the vectorized manipulation using the tensor dot in Theano. And one important step which is highlighted in yellow here is that you have basically a scene in 2D Grism spectroscopy, and for each one of these spatial bins you have a lot of 0 pixels, and they constitute a very, very large array. And if you want to tensor dot a very large array, your code will be run a lot slower. So before just dotting them, I identify non-zero pixels for each one of these spatial bins and tensor dot only the non-zero pixels. And that's what's going on in this highlighted part, and it leads to a 2 to 3 times faster code in total. So moving on, we have the HST photometry, which is calculated pretty much following the formula that I showed, and its likelihood is going to be a mixture model, and there is a lot of shuffling and reshaping going on here, and these are mostly because this PyMC3 basically mixture model accepts a very specific accepts basically a very specific dimensions for the arrays. And then finally we're going to have a Spitzer photometry likelihood. That's also pretty similar to the formula that I showed. And finally, after having all the elements in place, we can sample the posterior. So before going and fully sampling the posterior using no U-turn sampler or NOTs, I usually run a test using find map. And I'm not going to initiate anything using find map. I mean, this is just to make sure that I didn't mess up anything, because if you kind of like mess up anything in data reduction, you can easily find it out by finding a garbage solution in find map. And after that, I usually would like to run a very simple mean field approximation using ADVI. just to make sure that everything is still working. And then I'm going to sample the posterior fully using knots, and I'm going to be basically making 2 chains, and each chain contains 2000 rows, and I'm only going to be keeping the last 1000 rows. And then I basically perform kind of like a simple test of convergence in terms of R hat and the autocorrelation functions. And after making sure that the chains actually converge, I combine them. So I'm going to have 2000 rows from the posterior of each parameters from these 2 chains. And sometimes there are some slight issues with the sampler, and then if a problem arises, then I have to go and play with the knots keywords, and I usually bump up the max 3 depths to 11 and target accept to 0.95 to achieve the convergence. Anyway, so let's get back to the prior. And for the prior, as I mentioned, it's shown here, I use an autoregressive model with lag 2. So one way to test that is that go and generate a mock data and try to fit the mock data with this exact same methodology and see how well we can recover what we wanted. So we take the star formation histories, and the star formation histories are related to the weights beta that I showed you all along from a very famous cosmological hydrodynamical simulations called Illustris, and they are shown in the left panel here. And then we take those star formation histories, basically the weights, the betas, and then generate a mock data. We added the realistic noise of the HST and the Spitzer, and then try to fit them. And what we recover is in the middle panel. So in the right panel, we also show 5 examples from this around 100 simulations. And as you can see, the general trends in the data, except basically the various stochastic and sharp feature, can be recovered with our methodology. We also explicitly tested that we are able to recover the mock ages using our methodology without any biases. So this will justify that we can use this autoregressive model with lag 2 as a prior for star formation rate and eventually beta. So moving on, let's forget about the bins, and I'm going to show you the results for the global first. So the global means that I'm fitting the whole galaxy together, basically all the bins together. On the left, you can see the photometric results. So you can see the data with the black crosses. We have 5 HST bands and 2 Spitzer bands. And the posterior predictive distribution, the 1 sigma width of this distribution, is shown with the circle and kind of like the error bars. And as you remember, it was a mixture model that was going on for the HST filters and the Spitzer filters. So in order to show that, I just draw some samples for the beta from the posterior, but I don't weight them with the W's. And just show the distribution of those unweighted draws from the posterior as well with the line, as you can see here. And generally speaking, the data and the model match reasonably well. On the right panel, you can see the spectroscopic data with black, kind of like a step-like function. And the error bars, the 1 sigma error bars, are also shown with the gray bars. And the posterior predictive are also shown with blue lines. And as you can see, again, the data matches the model reasonably well. So we also fit the spatially resolved stellar populations, and we also have similar plots for the spatial bins, as you can see here. I just showed 5 of them. And again, the data and the model seems to be matching remarkably well. So moving on, in astrophysics, really nobody cares about beta, and this is really a zeroth level parameters. And the parameters that people are interested in are star formation rate and a parameter called a specific star formation rate. So a specific star formation rate has a unit of year inverse. So as a unit, it tells you this is the inverse rate of a star formation time scale. That means that if this specific star formation rate is higher, the galaxy is forming more and more stars, and if it gets lower, it forms less and less stars. And its posterior can be calculated from the posterior of the beta. So on y-axis, you can see the log specific star formation rate. On x-axis, you can see time, basically, or look back time, to be more specifically. And the way that this time works is that if you go to the right in this along the x-axis in this plot, you go toward the beginning of the universe, and then if you move to the left, you will go toward the time of observation for this galaxy. As you can see, there are two clear trends here. So this galaxy seems to be forming stars quite efficiently at the beginning of the universe, but its efficiency drops. But in the last 100 million years of its evolution, there's an uptick. And in astronomical terms, it seems that this galaxy is rejuvenating. But before talking about the rejuvenation, let me show you the spatially resolved analysis. So for a spatially resolved analysis, I basically fit two totally different models. And these two different models are defined by the way that I handled these nuisance parameters, okay? So I mentioned that for generating nuisance parameters, I used the posteriors from a software called Spitzer. So I generated two sets of posteriors by fitting the photometric data differently. I'm not going to really go into how I did that, but these are basically two different models, and I fit them just to make sure that I have a good handle on nuisance parameters. But as you can see, basically in the center, we kind of see the same pattern as we see for the global fit. So we have a decreasing specific star formation rate with an uptick in the last 100 million years of evolution. So the main parameter that we were trying to constrain was age, and here on the top panel you can see the median age. And I showed the median age for both a spatially resolved stellar population coming from two different models for SSP as well as the global analysis. And I also showed dust and metallicity as two nuisance parameters. And you kind of like see that we have kind of like a flat trend. So all the spatial beams in the inner probably 2 kiloparsec have about the same age. And the only exceptions are the two outer bins. And the other interesting thing about the two outer bins is that they seem to be these two different models that I fitted for a spatially resolved population shown by black and red also yield a little bit of different result outside 1 sigma. So we went back and checked these two bins, and it turned out that the data, the spectroscopic data for both these bins were strongly contaminated. And that's why that we think that we really cannot trust anything that is going down there, and basically all the patterns that we see in the ages and everything are probably dominated by the modeling assumptions and the priors, because we don't have really a quality data there. But in the inner, basically 2 to 3 kiloparsec that you can see here, corresponding to 5 central bin, it seems that the age is pretty much the same, and we don't have age gradients or flat age gradient. So the last thing that I'm going to be talking about is that when we ask whether this uptick that we see in the last 100 megayear of evolution, last 100 million years of evolution in the specific star formation rate is real. So one thing that we can see is to basically check whether or not this uptick and this upturn is statistically significant. So we calculated the posterior of different parameters, which is a star formation rate in the last 50 million years of evolution over a star formation rate in the last 150 million years of evolution. And if this parameter is greater than 1 or its logarithm is greater than 0, that means that we have kind of like an upturn or increasing a star formation rate. If it's 0 or less than 0, that means that the star formation is pretty much flat or even decreasing. And as you can see, with 1 sigma uncertainty, we have kind of like an increase in the star formation rate in the center in the last 100 million years of evolution. And this signal is actually a 2 sigma detection based on our posterior. So this tells us that this rejuvenation is statistically significant and also centrally concentrated, because if you look at the outer bins, they are consistent with 0. And we can also, one cool thing that you can do with strong gravitational lensing is that you can take that color image and make the unlensed color image, because gravitational lensing is gonna distort the shape and the morphology of the galaxy, but the unlensed image can be reconstructed using a lensing model. And if you do that, you immediately notice that there is a blue light kind of like at the center, as it is clear from the bottom a color image, in the color image in the bottom panel. And this blue light is basically diminishes once we move further out to the outer beams. And this blue light can be associated with all the younger stars that are formed at the center as a result of rejuvenation. So with this, I will finish my talk, and I just present a summary. So I introduced a novel Bayesian model. I called it Requiem 2D because it is developed for fitting the Requiem galaxies. And this code is designed to jointly fit a spectro-photometric data of Hubble and Spitzer space telescopes. And the model is a multi-level linear regression, and nuisance parameters are kind of like determined simultaneously through a Dirichlet process using mixture models. And it's able to handle the spatial resolution mismatch between the Spitzer and Hubble Space Telescope data. The model is fully implanted in PyMC theory, and every step of this computation of the posteriors is done in PyMC theory. And we also demonstrated that this model kind of like works for a real data for one of the galaxies in the Requiem survey, which was MRG S0851. And we also demonstrated that the most important prior in our study, which was a prior for star formation history, works for the Mach data generated from illustrious cosmological simulation and tuned for the specific observations that we are doing in the Requiem galaxies. Thank you.